Hey guys, in this video we're going to be taking a look at determining the total charge for a non-uniform volume charge density. So we looked at smaller dimensions before, and keep in mind here that the volume charge density rho is equal to Q divided by V. Okay, so rho is not constant because we are saying that it's a non-uniform charge density, and so I'm going to give you a function for rho, which could be a variety of different things, and the function for rho is going to be AR squared. Now, one thing to note here, that A is a constant, right? It's not area, so just keep that in mind so that you don't make a mistake on that. All right, so to get the total charge expression for this particular shape that we have here, we know that that's just going to be rearranging these variables to get rho times volume. Now, of course, rho is a function, and so it's going to vary. So let's take a look at how that varies in our shape. So the cylinder is length L, or height L, and its radius is R, right? And what this function says is that it gets more dense the further out you move. So at R equals 0 over here along the axis of this cylinder, there's no charge. And then it gets to have more and more charge as you move your way out. So it gets more and more dense on the way out. So anywhere along this axis, we'd have the same picture, okay? So this must mean that there has to be an insulating cylinder. Otherwise, the charge couldn't stay suspended the way that it is. It would move towards the outsides if it were a conductor. Okay, so in order to calculate the total charge with a non-uniform charge density, we need to write a differential form of this equation. So the differential form means that this becomes dq and this becomes rho dv. So the idea is if I can do the integral or sum up all the little pieces of q, I will get q total, and on this side I'll sum up all of the products rho dv for tiny, tiny little volume pieces. Now, if I substitute in rho into this, right, which is the function AR squared multiplied by dv, we see that the independent variable r of the density function doesn't match the variable of integration, right? So I want to change this. So what I'm going to say is that dv, okay, if we know that the volume of the sphere is pi r squared L, which is the area times the height, right? That dv is going to be equal to 2 pi r L dr. Okay, so if you think about going backwards to this direction, you would integrate that and you get this answer. So that's how I got this. So what I'm going to do here is I'm going to again change this to 2 pi r L dr. So I've got this whole string of stuff here, and I've got to simplify some things. I'll pull some stuff out from that are constants out of the integral. Before I do that, I want to figure out what my limits of integration are. So if you think about it, right, you're working your way from 0 all the way to the radius of this cylinder, and I'm going to call the radius big R just so that we can distinguish between these. Okay, so it's from 0 to big R. Okay, so let's pull out any constants. Okay, so I mentioned A is a constant, 2 pi is also a constant, right, and L. So A 2 pi L is all going to be pulled out front, and I'm going to integrate from 0 to R, and this will become R cubed, okay, once I've simplified that down, dr. Okay, so then what happens is I have to do the integration. Okay, so this is going to become 2 pi AL, and the integration will be R to the fourth over 4, evaluated from 0 to R. Make a little bit more room here. And then I need to plug in the limits, which it's not necessary to plug in the 0, right? So I'll have 2 pi a times L times big R to the fourth minus over 4 minus 0 to the fourth over 4, which I just said I wasn't going to do. I did anyway. And so once I actually factor back in all of this, I have 2 pi a times L times R to the fourth over 4. And then I can simplify that down just a little bit more over here, right? So I end up with pi ALR to the fourth over 2. And that, remember, is what we've been trying to do, is find the total charge. So what this does is we found the total charge of this cylinder in terms of the length, right? And it makes sense that the length and the total charge are directly proportional. So the taller that this is, right, the more charge you're going to have because there's more space. But it's still always going to vary the same way as we work our way out. Now keep in mind, the process will always stay the same of doing this, right? Integrating rho dV to get total charge. The thing that can vary is, of course, this, because the function could vary differently, right? You could have maybe as you work your way up, it gets more dense, or as you work your way down, it gets more charge dense, and so, you know, there's a variety of different things. So just familiarize yourself with this portion, right? This definition, I guess that's better, and then you can really do any combination of different charge density functions.